Hello, my name is Michal Neset from University of Olomouc, and I will present you our work about experimental noiseless quantum amplification of coherent states by use two-photon addition and subtraction. First of all, the main ingredients of our work is conditional addition and subtraction of photons. It can be described by annihilation and creation operators, and it's a fundamental quantum operation with many applications like engineering highly non-classical states of light, like GKP states or nonlinear squeeze states, but you can use it also for entanglement distillation and or compensation of losses in optical quantum communication, and also as we use it in noiseless quantum amplification. But the previous experiments were limited to conditional addition of only a single photon, but recently we experimentally implement addition up to 3 photons, and also we was able to make addition of 2 photons followed by subtraction of 2 photons into a single well-defined spatial temporal mode of light. Here you can see example of Wigner function of our prepared states where we performed conditional addition up to 3 photons. And this work was published last year. But this presentation is about noiseless amplification of coherent states. So how we can imagine it. We can describe noise properties of coherent state by its variances in phase space in x and p quadratures, and with some classical amplifier or deterministic quantum amplifier, we always add a noise into our signal. But with noiseless amplifier, in ideal case, we increase the amplitude of the state without adding any noise. And its operator you can see here, but unfortunately, this operation is unphysical. But in a work from Zavata, Firashek, and Bellini, they were demonstrated approximation of this noiseless amplification while they use a single photon addition and subtraction and make this amplification. But this works only for low amplitudes of coherent states. So how we can perform it? First of all, we need conditional preparation of single photons. For this, we can use heralded single photon source based on SPDC process. And then when we are able to generate a photon pairs, which usually cause signal and idler. And when we detect idler photon, it's herald our single photon. Also, we can add our coherent signal, and when this coherent signal is perfectly mode match with a signal photon, the heralding of idler also herald our operation of addition of single photon. Then we can add a highly unbalanced beam splitter to make a subtraction photon from our signal, and when we detect coincidences on these two detectors, uh, we herald our preparation of operation, addition, and subtraction of single photon. Also, uh, we can increase the pump power of our SPDC process, and it's increased the probability of generation of multiple pairs. So then we can use photon number observing detectors for heralding, and we can herald addition and subtraction to n photons. Here you can see our experimental setup. We use pulse laser in picosecond regime, and performed our addition and subtraction of photons. As you can see, we are able to herald addition up to 3 photons, and also we are able to herald subtraction up to 2 photons. And all our prepared states, we are measured by time domain balance homodyne detection with signals to noise ratio better than 12 dB and bandwidth better than 100 megahertz. And here you can see photography of our experiment. So how well we can prepare our states. Here you can see fidelity of preparation of our state when we use single photon addition and subtraction, and also for 2-photon addition and subtraction. And also you can see here a purity of our prepared states. Also you can see a Wigner function of our states. Picture A is for a case with 1 addition and 1 subtraction, and B is for 2-photon addition and 2-photon subtraction. Also, we can characterize performance of our noiseless amplifier. Here you can see gain of our amplifiers, and also we can describe the noise properties of it. So here you can see variances in X and P quadratures, and also the red lines is limits of deterministic quantum amplifier. And also, because these amplifiers works well only for low amplitudes of coherent states, it was proposed that you can use this interferometric scheme to enhance and boost the properties of amplifiers. Here is example when you use two paths, and here you use 2-photon addition and 2-photon subtraction in this scheme, and we compare it with our amplifier where we use 2-photon addition and 2-photon subtraction. And as you can see, the fidelities of states produced by this interferometric scheme or with our amplifier is quite similar, and the gain of these amplifiers are similar as well. So here I would like to thank my team and thank you for your attention.
Thank you very much, and we are open for questions again.
Thank you for your nice presentation. Actually, I have a very short question. How did you experimentally characterize the fidelity of the photon subtraction and addition?
You mean this fidelity?
Yes, yes.
Yeah, yeah. This fidelity is fidelity of preparation, and we calculate it with ideal state of this operation. Like this is fidelity between ideal state and our measured state in laboratory. Yeah, 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 yeah. We made after the homodynamic detection, we made a reconstruction of our states. Yeah.
I have one. So I was curious about this addition and subtraction of n photons. How does the success rate scale with n here?
Yeah, the success rates scale very badly. So for the two-photon addition, it's like 10 to minus 9. And yeah, yeah.
Okay.
I think it's
But you
my
managed with
limitation if in this process.
So you managed with 3 anyway.
Yeah, yeah.
Okay. There's a question.
The graph that you showed the gain in regards to n to yeah. So can you comment on like this why g is dropping down as you are increasing the mean photon number? So g is going down, right? As your mean photon number is increasing.
Can you repeat it, please?
So as the mean photon number is increasing, alpha, like the norm of
It's
alpha.
amplitude of our coherent state.
Yeah.
Yeah, yeah.
So why g is decreasing? Like, can you comment on that?
Because the approximation of this amplifier works well only for low amplitude of coherent states, and
Right.
when the amplitude is increasing, the gain of the amplifier is decreasing with it.
Okay. I'll allow myself one more because I'm curious. What happens if you first subtract and then add? Change the order.
Okay.
You work with very weak passes, so probably there's nothing to measure anymore.
Yeah,
First
yeah,
subtract.
yeah. I think so.
I just wonder if there is anything else. Okay. All right. Cool. So let's move on. Thank you very much.